Watch this inscribed triangle. As it shifts shape, proportions stay locked. We map it using capital letters for angles and lowercase for opposite sides, creating side-angle pairs. The sine rule equation proves dividing a side by its opposite angle's sine yields an identical ratio. Because this proportion is fixed, you only need to know the measurements for one complete side-angle pair. Once you have that starting pair, you can calculate the exact dimensions for the rest of the shape. This diagram shows two solid line segments, joined by a central hinge angle. We know these two sides and the angle between them, but the dotted line opposite the angle is unknown. Since we do not have a full side-angle pair, the sine rule cannot help us find that missing distance. Watch the dotted line change as the hinge opens and closes. To calculate that exact length, we use the cosine rule. It starts with the squares of the two known sides, b squared plus c squared. Then we apply a mathematical correction factor, minus 2bc cosine A, which adjusts the distance based on the specific hinge angle. When the hinge opens past 90 degrees, the cosine of the angle becomes a negative number. This negative value multiplies against the minus sign in the equation, turning the correction factor into a plus sign to accurately calculate the longer opposite side. We can also visualize this geometry through the projection rule. This animation shows a downward light source, casting shadows from the two slanted sides onto the flat base. By adding the lengths of those two shadows, b cosine c and c cosine b, we find the exact length of the base side. Whether we measure straight distances from a hinge or calculate shadows cast onto a baseline, the length of an unknown side is dictated entirely by the geometry of the sides and angles connected to it. To solve more complex problems, we use the semi-perimeter, denoted as S. You calculate it by adding the three side lengths together and dividing the total in half. This single value acts as a common component across several different triangle formulas. Here is how that variable is applied. We can find the sine and cosine of half an angle by taking our calculated S value and plugging it directly into these two half-angle equations. This allows us to find the interior angles using only the lengths of the three sides. When we stack the sine equation over the cosine equation to find the tangent, the math simplifies. The common b, c denominators cancel out, leaving a single formula for the tangent half-angle. It is a direct mathematical result of dividing the first two equations. There is also the half-angle ratio rule. This is a specific tool for problems that provide the sum or difference of two side lengths, connecting those side relationships directly to the half-angles. These identities are not independent rules to be memorized in isolation. They are all variations built from the same foundational side lengths and the semi-perimeter. We typically find area using 1/2 base times height. However, if the height is unknown, Heron's formula allows us to reach the same result using only the side lengths and the semi-perimeter. Both methods describe the same physical space. If a triangle has sides of 5, 6, and 7, we find our S value of 9. We plug that 9 into the square root, subtract each side length, and multiply the results. This gives us a final area of 14.70 square units. This flowchart shows the logical progression of the triangle language. The side lengths define the semi-perimeter. That value determines the half-angles, and the half-angles define the total area. Most triangle problems can be solved using these three primary tools. The sine rule handles side-to-angle proportions. The cosine rule finds missing sides, and Heron's formula calculates the area. These 8 equations are not separate math problems. They are interconnected ways of describing the same geometric truth, that every part of a triangle is determined by the parts surrounding it.